Imagine you're peering through a microscope at a tiny network of channels etched into glass, no pumps, no moving parts, yet you watch tracer particles drift preferentially in one direction as if an invisible hand were sorting them. Welcome to the world of the microfluidic Maxwell's demon, where clever, passive structures seem to rectify Brownian motion, hinting at a one-way ratchet that does work and flirts with the second law of thermodynamics. How can random thermal jostling become directed motion? In these devices, asymmetric obstacles like funnel-shaped posts or sawtooth ratchets bias the random collisions of particles so they're more likely to slip forward than backward. Each bounce off a slanted wall gives a tiny push in the preferred direction, and over thousands of collisions, you see a net flow, macroscopic work springing from microscopic chaos. Is this a loophole in thermodynamics? Not really. Every demon loses more energy in thermal fluctuations and viscous drag than it extracts, preserving the second law when you count the full energy budget. But at the micro scale, these ratchets teach us that entropy and work blur. They show how careful geometry can harvest ambient noise to power micropumps or concentrate particles without external power feeds. What real-world feats have been achieved? In one experiment, researchers used a honeycomb of funnel channels to concentrate DNA molecules from a dilute solution, trapping them at the narrow end until a laser pulse released a burst of single-molecule analysis. In another, bacterial suspensions flowing past asymmetric posts generated a steady circulation, living Maxwell demons turning microbial wriggles into fluid currents. Could you build a self-provided lab on a chip? Imagine a point-of-care diagnostic device with no bulky pumps, just a pattern chip where blood cells drift, sort themselves, and deliver biomarkers to sensing wells. All powered by their own thermal jiggles. That's the dream driving microfluidic demon research, turning inevitable motion. So what's the big takeaway for beginners? The microfluidic Maxwell's demon doesn't overthrow physics. It reveals its subtle beauty at tiny scales, where geometry, fluctuations, and dissipation dance together. By mastering asymmetric microstructures, engineers can craft devices that harness randomness, illustrating that even the most basic thermodynamic laws become rich, nuanced guides when you shrink down to the world of molecules. A microfluidic Maxwell's demon uses asymmetric channel geometries or surface patterns to bias the random, thermal-driven movement of colloidal particles or molecules, causing net transport in a preferred direction. These passive microstructures, ratchet-like barriers or funnel arrays, rectify Brownian motion without external power input, appearing to perform work. At first glance, this seems to circumvent the second law of thermodynamics, which forbids extracting work from equilibrium fluctuations alone. In reality, subtle energy or information costs in fabrication, particle wall interactions, or maintenance of boundary conditions restore compliance with thermodynamic principles. An array of triangular posts in a nanochannel directs gold dynam quadrates preferentially to one side under uniform thermal agitation, concentrating them over time. It's like a one-way turnstile that lets people wander through randomly but collect slightly more on one side, yet the turnstile itself subtly consumes energy in its bearings. The second law states that in an isolated system, entropy cannot decrease. Microscopic work cannot be extracted from thermal noise without a compensating energy input. At microscale, however, thermal fluctuations dominate particle motion, and spatial asymmetries can transiently bias trajectories. Passive rectifiers exploit these fluctuations but require non-equilibrium boundary conditions, such as maintained temperature gradients or concentration differences, to generate sustained flux. Thus, they do not truly violate the second law, as the overall entropy, including that of the surroundings or device fabrication, still increases. A nanofluidic diode shows net ionic current under zero average voltage due to asymmetric pore geometry, but only if ion concentration gradients are maintained. It's like a garden wind vane that spins more one way in a variable breeze, but only because the breeze itself is not perfectly random and uniform. In these devices, channel walls impose spatially varying energy barriers, sawtooth or ratchet potentials that break left-right symmetry. Brownian particles climb and descend these barriers randomly, but the asymmetric shape makes forward hops slightly more probable than backward ones under non-equilibrium conditions. The result is a net drift even without a net external force. Careful design of barrier height and spacing tunes the rectification efficiency. Colloids in a microfabricated funnel array drift toward the wide end when subjected to oscillatory flows due to the asymmetric geometry. It's like marbles on a board with shallow ramps leading one way and steep walls the other. If the board vibrates randomly, more marbles roll down the gentle ramps. Entropic barriers arise where confinement changes accessible microstates. Narrow constrictions reduce entropy relative to wider regions. Particles preferentially move toward regions of higher entropy, wider spaces, creating a net flux if asymmetric. This is equivalent to an effective force despite no real potential energy gradient. Maintaining a concentration difference across the ratchet ensures continuous operation. DNA molecules in an asymmetric nanopore drift preferentially from narrow to wide cavities under uniform temperature, driven by entropic forces. It's like preferring to stand in a spacious room rather than a cramped hallway. The doorway's shapes guide your wandering. A true Maxwell's demon requires measurement and feedback, but microfluidic ratchets rely solely on thermal fluctuations plus static geometry. However, to sustain directional flux, the system must be held out of equilibrium via temperature gradients, oscillatory flows, or chemical potential differences. Without these driving forces, rectification ceases and the net current returns to zero. Thus, fluctuations are harnessed only in concert with non-equilibrium conditions. A thermal ratchet using periodic temperature modulations enables continuous particle pumping in one direction. It's like water flowing over asymmetric ripples only when the river level is constantly replenished upstream. Rectification efficiency depends non-linearly on particle size relative to barrier dimensions. Too small and particles diffuse freely, too large and they cannot surmount entropic barriers. There's an optimal size range where directional drift peaks. Similarly, drive amplitude, flow rate, or temperature swing must exceed a threshold to overcome barrier heights. These nonlinear dependencies allow selective separation or sorting by size or motility. Microparticle ratchets separate bacteria from smaller molecules by tuning funnel dimensions to preferentially pump only the bacteria. It's like a sieve that only lets grains of a certain size pass under a vibrating screen. Although passive nanoratchets cannot generate net work from equilibrium, they can convert externally supplied fluctuations, like random flow pulses, into directional transport, enabling microscale pumps and actuators. Such devices could harvest ambient vibrational energy to power lab-on-a-chip components without integrated electronics. They also inspire designs for self-propelled microparticles in targeted drug delivery. A microfluidic pump uses intermittent pressure oscillations and asymmetric valve geometries to move fluid continuously in one direction. It's like a child's play pump toy that uses back and forth motion to draw water up through a one-way valve system. Creating reliable asymmetric structures at submicron scales demands high-resolution lithography or controlled self-assembly, both of which can be expensive and yield variability. Surface fouling and blockages by debris or biomolecules degrade performance over time. Integrating these ratchets into larger fluidic circuits requires careful matching of flow resistances and compatibility with other components. Robust materials and anti-fouling coatings are essential for practical deployment. Silicon-based ratchets lose efficiency in protein-rich media unless coated with PEG to resist adsorption. It's like building a narrow canal in the desert. It works until sand and weeds clog the channel. Advances in dynamic ratchets, where barrier shapes or environmental conditions are actively modulated, could approach true feedback-based demons without explicit information processing. Coupling synthetic molecular motors with passive structures may yield hybrid systems that amplify rectification. Theoretical studies of fluctuation theorems and stochastic thermodynamics continue to clarify entropy budgets in these devices. Ultimately, microfluidic Maxwell's demons deepen our understanding of thermodynamics at the nanoscale and guide the design of efficient nanomachines. Researchers are exploring light-activated ratchets where illumination patterns toggle barrier heights to steer particles on demand. It's like programming a sequence of tilts on a pinball machine to guide the ball precisely through the maze without kinetic launchers.